How does structured streaming work? First, what is structured streaming? Well, structured streaming is a new real-time streaming framework proposed by Spark 2.0, which is specifically used to process real-time data streams. Next, let us understand the programming model of structured streaming. The key idea in structured streaming is to treat a live data stream as a table that is being continuously appended. This leads to a new stream processing model that is very similar to a batch processing model. You will express your streaming computation as standard batch-like query is on a static table, and Spark runs it as an incremental query on the unbounded input table. Let's understand this model in more detail. Now, consider the input data stream as the input table. Oh. A query on the input will generate the result table. Every trigger interval, say, every 1 second, new rows get appended to the input table, which eventually updates the result table. Whenever the result table gets updated, we would want to write the changed result rows to an external sink. The output is defined as what gets written out to the external storage. The output can be defined in a different mode. Note that each mode is applicable on certain types of queries. This is discussed in detail later. Ha! To illustrate the use of this model, let's understand the model in context of the quick example above. The first line's data frame is the input table, and the final word counts data frame is the result table. Note that the query on streaming line's data frame to generate word counts is exactly the same as it would be a static data frame. However, when this query is started, Spark will continuously check for new data from the socket connection. If there is new data, Spark will run an incremental query that combines the previous running counts with the new data to compute updated counts, as shown below. Note that structured streaming does not materialize the entire table. It reads the latest available data from the streaming data source, processes it incrementally to update the result, and then discards the source data. It only keeps around the minimal intermediate state data as required to update the result, e.g., intermediate counts in the earlier example. This model is significantly different from many other stream processing engines. Many streaming systems require the user to maintain running aggregations themselves, thus having to reason about fault tolerance and data consistency at least once, or at most once, or exactly once. In this model, Spark is responsible for updating the result table when there is new data, thus relieving the users from reasoning about it. As an example, let's see how this model handles event time-based processing in late arriving data.